Good afternoon. Today we're going to be talking about 45, 45, 90 right triangles, or isosceles right triangles. And we're going to start by taking a look at the three triangles located on your guided note sheet. So if you would please take out your guided note sheet and join me where it says use the Pythagorean theorem to find the missing lengths of the following triangles. So we're looking for missing lengths, which usually means that we're looking for sides. So we're going to take a moment, we're going to find the missing sides of these right triangles using the Pythagorean theorem. We know the Pythagorean theorem can be used on right triangles, and all of these triangles are right triangles because we see the right angle box in the corner of each of these triangles. Pythagorean theorem, we remember from earlier this week, is a squared plus b squared equals c squared. And we know that a and b are what we call the legs of a right triangle, and those are going to be the two sides that make the right angle. So this would be a leg, and this 5 squared root of 2 would be a leg. The hypotenuse is going to be represented by the letter C, and the hypotenuse is the longest side of a right triangle, and it's also the one located directly across from our right angle. So in this triangle on the upper left-hand side, we're going to find that 10 is our hypotenuse. So we're going to plug these side lengths that we have into our Pythagorean theorem to find the side length that we're missing. In this case, it's going to be the bottom side, which we're going to call x. Looking at this triangle, we have a hypotenuse and we have a leg, and we're missing another leg. We know from the Pythagorean theorem that because we're adding the squares of the legs, addition, order doesn't matter. So we can call either 5 squared root of 2a or b, and we're fine either way. So I'm going to work on to the left-hand side of this, and I'm going to write a squared plus b squared equals c squared. I'm going to go ahead and plug in 10 for c, that's my hypotenuse, and I'm going to call 5 squared root of 2a for right now. If you called it b, that's all right. Now we're going to simplify. We're going to start with 10 squared. We know that when we square something, we're multiplying it by itself. So 10 times 10 is 100. So 10 squared is 100. 5 times the square root of 2 squared. Because these two terms are multiplied, what we're going to do is we're going to share the square. Basically, we're going to distribute it to each of these numbers. So I'm going to do 5 squared, which is 25. And I'm going to multiply that by the square root of 2 squared. Square root of 2 squared is square root of 2 times another square root of 2. Square root of 2 times square root of 2, effectively the square and the square root cancel, and we're left with just the number 2. 25 times 2 is 50. So on the left side of my equation, I get 50 plus b squared equals 100. My goal is to get b by itself, so first I have to subtract 50 from each side. When I do that, I end up with b squared on the left and 50, 100 minus 50, on the right-hand side. To get b alone, I'm going to undo the square with a square root, and I'll end up with b equals the square root of 50. We like to simplify squares, and in this case, this square root it is possible to simplify because it does have a perfect square factor, and that perfect square is 25. So I'm going to say that the square root of 25 times the square root of 2 is equal to the square root of 50. Square root of 25 simplified is 5, so I'm going to have 5 square root of 2 equals b. So my missing leg x is going to be 5 times the square root of 2. I'm going to go ahead and circle that in color so it's a little bit easier for us to see. So I have my missing side is 5 times the square root of 2. The leg that I was given was also 5 square root of 2, and my hypotenuse was 10. Now that we found the missing side on our upper left-hand triangle, let's move to the upper right-hand side. Looking at the upper right-hand side, I want you to take a moment and I want you to label which sides are the legs and which side are the hypotenuse. Pause the video if you need to. Alrighty, hopefully you wrote that 2 square root of 2 was a leg, the other 2 square root of 2 was a leg, and my missing side is the hypotenuse, and we're going to call this y for right now. Looking at this, I know that 2 square root of 2 and 2 square root of 2 are legs because they are on either side of my right angle, and they are the sides that they are essentially the rays that form my right angle. I'm going to use my Pythagorean theorem, again, a squared plus b squared equals c squared, where c is my hypotenuse, to find my missing sides. So in this case, I'm going to, both my legs are identical, so it doesn't matter which one I call a and b, they're the same. So I'm going to say 2 square root of 2 squared plus 2 square root of 2 squared equals my hypotenuse squared. And we're representing our missing hypotenuse with the letter y, so y squared. we are going to distribute our square because these two numbers are multiplied again. We can share the square, and we have to share the square with each term. So in this case, we're going to do 2 squared, which is 4, times the square root of 2 squared. Again, from before, that's 2. 2 times 4 is 8. And we have the same thing again for b squared, so we're just going to put another 8 in for that. That equals y squared. Now we simplify the addition. 8 plus 8 is 16. 16 equals y squared. To get y by itself, we are going to take the square root. Okay. That leaves y on the right and the square root of 16, which is 4, on the left. So our hypotenuse is 4. I'm going to go ahead and I'm going to circle these so it's a little bit easier to see. Hypotenuse is 4, and my legs are each 2 times the square root of 2. Let's take a look at our next triangle. Our next triangle, we notice we are missing a leg. We have one of our legs, and we have our hypotenuse. It's across from our right angle. So let's take a moment, use our Pythagorean theorem. I want you to write down the Pythagorean theorem on your own first. Pause the video if you need time. Alrighty, you should have written a squared plus b squared equals c squared, which is our Pythagorean theorem. And remember that c is always our hypotenuse. So I'm going to go ahead and I'm going to substitute for c 6 times the square root of 2. And remember, in the Pythagorean theorem, it's leg squared plus leg squared equals hypotenuse squared. So I'm going to have to square that hypotenuse. And that's going to equal to my leg squared. We're going to call this leg, my missing leg, z. So z squared plus, my other leg is 6. 6 squared equals 6 square root of 2 squared. So let's go ahead and simplify this. Z squared is going to stay z squared for the time being. 6 squared is 36. And again, I'm going to have to share my square with each number inside the parenthesis because they are multiplied. So 6 squared is 36. Square root of 2 squared, the square root and the square cancel, and I'm left with 2. So it's really 36 times 2. 36 times 2 is 72, so 72 equals z squared plus 36. Our goal is to get z by itself, so first we have to subtract 36 from each side. When I do that, I end up with z squared alone on the left and 36 on the right. Now, to get z isolated, I'm going to take the square root, which is inverse operation. I'm canceling out my square. What I do to one side, remember, I have to do to the other. So when I take the square root on the left side, I also take the square root on the right side. I'm left with z by itself on the left, and the square root of 36 is 6. So my leg is 6. So I'm going to go ahead and I'm going to circle and color my sides. So let's take a look at these triangles for a moment. I noticed that each of these triangles has a right angle and a 45-degree angle. And that is true for all of them. But we have a missing angle in each one. We know from the triangle sum theorem that all of the interior angles of a triangle have to add up to 180 degrees. So if I take this triangle on the upper left-hand side, I know that 180 degrees is equal to my 90-degree angle plus my 45-degree angle plus my unknown angle, which I'm going to call W. Okay. To get W by itself, I'm going to add 90 and 45, which is 135, and then I'm going to subtract it from each side of the equation. When I do that, I'm left with W alone on the right and 45 on the left. So my missing angle is 45 degrees. We'll notice that this makes an isosceles triangle. The base angle theorem says that if we have two congruent base angles, we are going to end up with legs that are identical. So though this triangle is called a 45, 45, 90 right triangle, it's also called an isosceles right triangle because we have two legs that are identical. Let's see if this holds true for this triangle as well. Upper right-hand corner, I see a triangle with a 90-degree angle, a 45-degree angle. Well, 90 plus 45 plus another 45 is how we hit 180 degrees. So this is also a 45, 45, 90 triangle, and we have two congruent legs. The legs are 2 square root of 2 as the measurement for each of them. Looking at our bottom triangle, We see 45, 90, and that means that our missing angle also has to be 45 because that's the only number that when added to 90 and another 45 makes 180 degrees. It makes our triangle sum theorem true. We will notice that we have our two 45-degree base angles, and the legs are congruent as well. So these are all isosceles triangles, isosceles right triangles, and you will notice that they all have 45, 45, and 90-degree angles. So a 45, 45, 90 triangle is the same thing as an isosceles right triangle. Now, looking at these, we can notice some patterns. The first thing I noticed that all of these triangles are 45, 45, 90 triangles. So I'm going to say all triangles are 45, 45, 90 triangles, and another name for that is an isosceles, I-S-O-S-C-E-L-E-S, isosceles, right, triangle. So we're going to use those two terms interchangeably. Okay. You'll notice that the instructions at the bottom of your guided note sheet ask you to choose 3 patterns that you observe in the 3 right triangles and list them below. I want you to come up with 3 patterns that you notice. I would, as a hint, tell you to look at the legs, compare the legs to each other, and then compare leg to hypotenuse, and then hypotenuse back to leg. Tomorrow in class, we're going to go over those 3 patterns that you observed, and we will practice using them. The reason why isosceles right triangles are so important is because an isosceles right triangle is half of a square. A square has 4 90-degree angles. It has 4 congruent sides. If we were to draw a diagonal from corner to corner, we're going to cut that 90-degree angle into 2 45-degree angles. And we're going to find that we have 2 congruent legs, which makes it an isosceles right triangle. This shape is super important. It's going to be really common in architecture, in construction, in any kind of woodworking or building project that you might take on, as well as crafts, art, and sewing. So it's super common, and knowing these relationships and these patterns allow us to really quickly find the lengths of sides without having to actually take out a tape measure and measure it or use the Pythagorean theorem. We'll be able to find them super quickly, which will come to benefit us when you take SAT or ACT tests, as well as your end of course exam in May for this class. Tomorrow in class, we will be working on application problems for 45, 45, 90 triangles. So we'll be putting this into practice, and we will also be making a visual with a group so that you have a model of what the relationships are that you can refer to until you're more familiar with these and you have them memorized. Thank you for watching, and I look forward to seeing you in class tomorrow.